Let's begin with a single point. A point has 0 dimensions. If we extend it into a line, how many points will fit on that line? An infinite number. If we extend the line into a plane, how many lines will fit into that plane? An infinite number. And if the plane is extended into a cube, how many planes will fit into that cube? You guessed it, an infinite number. Now there's a pattern here. Higher dimensional spaces contain an infinite number of lower dimensional spaces. Thus, we can predict how many 3D cubes will fit into a 4-dimensional space. Once again, it's an infinite number. Submitted for your approval, the Calabi-Yau used by string theory to represent the 6 curled-up dimensions of space. These dimensions are so small we can't detect them, but if somehow we could blow up a patch of space, we might see something like this. Here, 3D space is represented by the 2D grid plane. The Calabi-Yau seems like a small bit of space on the Planck scale, but that tiny 6D space holds enough 3D space to contain our entire universe, and then some. Infinite space implies infinite ground state energy. If the particles of the Standard Model consist of these spaces, they would have infinite mass and/or energy. Such is not the case. There is a way string theory gets around this problem. It gives each curled-up dimension a one-dimensional extent. The black line in this diagram represents 3D space. The loop represents an extra curled dimension. The blue represents a point particle or string, and the red is a giant 3D object. The blue can easily access the higher dimension, but the red can't. But there's a flaw in this model. There is more than one point in this universe that has a curled dimension. And basic geometry tells us that where there's at least 2 points, there's a line. In this case, each line really represents 3D. So any object in this universe can access the higher dimension. Of course, this model really has an infinite number of points, so an infinite number of lines exist. Each line is a parallel universe, completely accessible to the largest objects. If higher curled-up dimensions really exist, they would have been discovered ages ago. The extra dimensions of string theory are, at best, an abstract idea.